The ability to measure dense 3D scene motion has several applications, including user interfaces, augmented reality, and robotics. In this paper, we propose a novel approach for recovering 3D scene motion from light field gradients. Our approach is based on the derivation of a new linear constraint, the ray flow equation, which relates the dense 3D motion field of a scene to gradients of the 4D light field. This equation is underconstrained because there are 3 unknowns per equation. Therefore, we need to impose additional constraints to recover motion. We observe that the ray flow equation has a similar form as the classical optical flow equation. Both are underconstrained linear equations. By exploiting the similarity between ray flow and optical flow, we developed 2 families of 3D motion recovery methods, based on the local Lucas-Canati optical flow and the global Horn-Schunck optical flow. We also develop a combined local-global ray flow method that combines the benefits of both families. Please see the paper for algorithm details. Next, we show 3D motion recovery using the proposed techniques. We use a LiTRO-Illume camera to capture light fields. In the first experiment, the scene consists of a static background and a single moving object, a playing card. The moving object is mounted on a controllable translation stage for ground truth comparisons. We calibrate the LiTRO camera and extract the central 9x9 sub-aperture images as input. Here we show a 3x3 subset. Scene motion consists of the card moving diagonally in the XZ plane by 2.4 mm. The light field gradients are computed by a Gaussian filter combined with a finite difference filter. Our method can recover the scene motion with sub-millimeter precision along all 3 axes, as shown in the figure. We compare our method with a state-of-the-art scene flow method that estimates Z motion by explicitly computing depth. Notice that the 2 methods perform similarly well for X and Y motion. The existing method cannot recover the Z motion accurately because the errors in depth estimation are large compared to the millimeter scale motion along Z. The proposed ray flow method estimates the Z motion directly, thereby achieving higher accuracy. This scene has multiple independently moving cards with overlapping boundaries. Here we compare our method with another existing scene flow method that computes Z motion as the change in estimated depth. Our method again estimates the Z motion more accurately. This scene consists of a rotating spherical object. The gradually changing XZ motion is correctly estimated by the algorithm. This experiment shows our method's capability to recover motion in a natural environment. The mug on the left is picked up by a hand. Our method preserves the motion boundaries despite occlusions. This example shows the quivering branches of some plants. Our method can compute the motion of the branches despite occlusions and complex shapes. This scene consists of a person waving his hand. This is a challenging example because the background includes prominent glass reflections and sizable textureless regions. Our method can still recover the movement of the hand. Here we show a failure case of our method. This example features many shadows cast on a textureless tabletop. Because the brightness constancy assumption is violated, none of the 3 methods can estimate the motion boundaries exactly. In summary, we derive a linear equation that relates the 3D scene motion with light field gradients. By adapting techniques from optical flow research, we propose novel approaches for recovering 3D motion. Initial results show the proposed methods can recover motion for a wide range of scenarios. Light field cameras have long been studied for depth sensing and image refocusing. This paper takes the first steps towards positioning light field cameras as effective motion sensors, in addition to their depth estimation capabilities.